Welcome to solverfy.
We can find the energy for part A. This would be equal to the Planck's constant multiplied by the speed of light divided by the wavelength lambda. And this would be equal to 1,240 electron volts nanometers. And then this would be divided by 10.0 times 10 to the negative third nanometers. This is giving us 124 kilo electron volts. Now for part B, we can find the kinetic energy gained by the electron. This is going to be equal to the energy decrease of the photon. So the kinetic energy gained would be equal to the change in energy of the photon. This would be equal to the change in hc over lambda. And this is equaling hc multiplied by 1 over lambda minus 1 over lambda plus delta lambda, that change in wavelength. And so we can then say that the kinetic energy gained will be equal to hc over lambda multiplied by the change in lambda divided by lambda plus the change in lambda. And so this would be equal to the energy divided by 1 plus lambda divided by delta lambda. And we can then solve. So for part B, the kinetic energy gained would be equal to the energy divided by 1 plus lambda divided by the lambda of the Compton collision minus 1 over cosine of phi. This is going to be equal to 124 kilo electron volts divided by 1 plus 10.0 picometers divided by lambda of lambda sub c being 2.43 picometers multiplied by 1 minus cosine of 180 degrees. And so we find that the kinetic energy gained is going to be equal to 40.5 kilo electron volts. This would be our answer for part B. For part C, we know that here, because energy imparted to the electron, we can say that the photon would have knocked the electron out of its orbit. So because of the energy imparted by, oh wait, my apologies. Imparted to the photon, the photon would have knocked the electron out of its orbit. Therefore, it is impossible to view an atomic electron with such a high energy photon. That is the end of the solution. Thank you for watching.